we were proving Friesecke James Muller theorem, and this is where we were. So we had U from some region, we took it just to be the unit ball for simplicity, into R2, with this hypothesis that the integral of the distance squared of the gradient away from rotations we're going to call it epsilon, is equal to epsilon. We did the following reductions to this situation. We first observed that if we take the divergence of the cofactor of the u minus the u, this thing is equal to minus Laplacian. As always, we mean divergence of the first row, divergence of the second row is Laplacian of the first coordinate, Laplacian of the second coordinate. This allowed us to define z that solved the same thing, that minus Laplacian z was equal to the divergence of the cofactor of the u. The pen. Minus du, like this, and u equals 0 on the boundary of the ball. And we could test z, this Laplacian of z with z itself, integrate by parts twice, and we found that, let's just put it here, that the L2 norm of the gradient of z on the ball was less than epsilon, which means we can, without any cost, take away z from u and have the same hypothesis here, which allowed us just to work with this function w. So we defined w to be u minus z. It has the same hypothesis. It is harmonic by this assumption. Yeah? And using this identity that we have for harmonic functions, that if we take the Laplacian of the gradient of w squared, this is equal to 2 times the second gradient of w, like this. So using this, we could it's this, gradient squared like this. We could actually use this to get an integral estimate on how big the second gradient of w was, and it was of the form like this. So we had to have a cutoff function, so we have to now be inside a smaller ball of size 1/2, but we ultimately could show that this thing was less than epsilon. So in particular, by Holder's inequality, we can take the L1 norm of the second gradient and it's less than, and there's always a constant in this game, it's less than the square root of epsilon. Okay. And my question for you was to think about how we could go from this hypothesis to showing that we actually have an L infinity bound, and therefore that on a small subball, we have that the gradient of w is close to 1 fixed rotation. So you've been thinking hard all weekend about this. Give me some suggestions. Why is this true? We are going to use the mean value property, which says that we can pointwise represent something as its integral. Yeah? So I showed you the mean value property, or stated it on the boundary of the ball. I briefly said it's also true inside a solid ball, and let's just see that. So if, let's just put a sidebar here. So if f is harmonic, then we know that f of x is equal to 1/2 pi r, the integral around the boundary of the ball of radius r of x of, that's right, f of z, the h1 of z, like this. This is the mean value property. Yeah? But What does that mean? We can multiply both sides by r, so we have 2 pi r. F of x is equal to this thing. And we can now integrate in R. And integrating in R might be somewhat unfamiliar to you because what we're using is a version of Fubini's theorem called the Courier Formula. So Fubini's theorem, we integrate lines up. So we take some region and we take all the lines and we take all parallel lines and we integrate them up to find the integral over some region. It's also the case that we can integrate on things like the boundaries of balls, like this. And by integrating up the boundaries of balls, we can also find a solid integral over a two-dimensional domain, such as a solid ball. And that's what we're going to do here. So this is called the Courier Formula. It's quite a deep theorem, but for the case of just the boundary of the ball, it's actually not too hard to prove. You can also just think about this in terms of integrating in polar coordinates, which you've already seen. So the Courier Formula. I mean, this would be a nice exercise to prove just for yourself. Just take a smooth function and take the Riemann sum and it's past the limit. See that this is true. If we integrate from 0 to, let's say a of 2 pi r f of x dr, that's the same as integrating 0 to a, integrating around the boundary of the ball of radius x, f dh1, z, and then this is dr. And this, I claim by the Courier formula, is the same as the integral around the solid ball of radius a around x, f of x dx. And here I mean the two-dimensional integral around the solid ball here. Maybe out of consistency, I'll put a double integral just to emphasize that this is a two-dimensional integral. Okay. So this part here, this equality is the Courier formula. Yeah? And then this part here, we can just pull out the f of x, and then we integrate this thing, and we're just going to get a squared pi like this, right? Which therefore means we can divide by this, and we have that f of x is equal to the average over the solid ball, like this. We've used x already. Let's use x. Let's use y maybe. Like this. Okay. And you might have seen this already as just the statement of the mean value theorem, but the mean value theorem, as I introduced it in complex analysis, I introduced it for the boundary of balls, because that's the form you see it in the Cauchy integral formula. Given that, and given this, we're now in a strong position, right? We're now in a strong position because we know that W is harmonic, yeah? And therefore all the partial derivatives of W are harmonic, yeah? Because it's smooth, we can just differentiate, swap the order of differentiation. And then this thing right here means the following. So take any x inside the ball of radius 1/4. So when it's around 0, I'm never putting 0 here. If you just see a ball of some radius without anything, it's always a ball around 0. You know? So take any x inside this ball, and then if we consider this thing, the integral around a ball of radius 1/4 around x of this guy, I mean, it's obviously contained within the ball of radius 1/2 around 0, so it's still less than c times square root of epsilon. Yeah? But we also know by the mean value property over the solid ball like this, we have that this thing is equal to the integral average of the ball of radius 1/4 around x of second gradient of w y dy. So now I'm no longer writing double integrals, so maybe actually I'll just get rid of this because I want to try and be consistent. So from the context of the domain we're integrating over, you're going to have to identify if it's an integral over a path or if it's an integral over a solid thing. And just stop me and ask me if anything is unclear. Usually we're going to be integrating over solid things. Okay, so this is just a statement of this thing right here. Yeah? And then we can just put absolute value signs throughout, right? So put the absolute value signs inside this thing. Like this. Yeah. And the average, when we're dividing by the area of the ball of radius a quarter, so that's pi over 16, and that's just a constant. We don't care about it, so we're just going to absorb it inside this constant when we do the final step, right? Or when we do this step, so we still have this is less than this thing, and that's exactly what we want, because that's true for any x inside the ball of radius 1 over 4. Huh? So in other words, so the an infinity norm, which means the supremum over all values of this thing, I'm going to write it like this. Yeah, consistent. Is less than constant square root of epsilon. All right, so that's pretty good news, right? So everything is smooth. The second derivative is uniformly bounded above by epsilon, right? Which means that whatever gradient we take inside the ball of radius a quarter, then the distance between that gradient of w and any other gradient inside the ball of radius a quarter, should have said a quarter, has to be less than square root of epsilon. Yeah? Yeah? So since we know that the overall integral of the distance of the gradient of w away from rotations in the L2 sense is less than epsilon, we can pick one guy inside the ball of radius a quarter such that the distance of that gradient away from rotations is less than constant times epsilon. Yeah? Yeah? And therefore, the total for every single one of these gradients, the distance of the gradient away from that rotation is less than a constant times square root of epsilon. Do you see what I mean, people, or shall I write that out carefully? Thumbs up if you see what... Okay. Yes. So from this thing and from this thing, we have the following. So let's call this thing 1 and call this thing 2. So 1 and 2 imply that the integral of the ball of radius 1 around the ball of radius 1 of the distance squared of the gradient of w away from rotations dx 1 over 2 is less than constant times epsilon. Yeah? Cool. So pick some x0 belonging to the ball of 1 over 4 such that the gradient of w of x0, let me write it like this, such that the distance of the gradient of w x0 away from rotations is less than constant times epsilon. We must be able to find such an x0, since if that wasn't true, then this thing would have to be false by Holder's inequality. All right, so let 0 be such that gradient w of x0 minus r0 is less than c times square root of epsilon. There is one, yeah? And then we also know that for any other gradient inside the ball of radius a quarter, the distance of the gradient of w away from this gradient has to be less than square root of epsilon by this thing, yeah? So we're going to have that sup of the distance of the gradient is minus r0 x belong to the ball of radius 1 over 4 is less than constant times square root of epsilon. Yeah? And without loss of generality, take 0 to be just the identity. So we can just compose with an affine function in the interior and have that this thing is just the identity. So this comes for free essentially. So let's draw a picture of what we have here. So we have the identity rotation like this, yeah, and we have a ball of radius. I'm going to draw it somewhat big. We have a ball of radius square root of epsilon. That's really a bad ball. Let me put the identity right here. This is the identity. And then this thing is constant times the square root of epsilon, like this. Yeah? And we have that all the gradients of W on the subball of radius 1/4 around 0 live inside this ball around the rotations. Yeah? That's what this thing says. This ball is so bad, I want to adapt it. Okay, cool. Well, now we start to be somewhat happy. Because what are we going to do? So let's take the tangent space to the space of rotations at the identity, like this. This is the tangent space. So what is that space? So let's just differentiate d by dt of cosine of t minus sine of t, cosine of t, like this. And what's that going to be? Minus sine of t minus cosine of t, cosine of t, sine of t. So if we take the tangent space at 0, so at t equals 0, we have that this thing of this thing is what we call a skew-symmetric matrix. It's this thing, minus 1, 1, 0. Okay? Which belongs to skew 2 times 2, which is the set of all matrices belonging to 2 by 2, such that when we take the transpose is equal to minus the matrix. Okay? That's what we call a skew-symmetric matrix. Yeah, if you take the transpose of this thing, then it's minus what it was before. Yeah? Cool. All right, and if you think about this for a second, or maybe a couple of seconds, what can this space of 2 by 2 matrices look like? What's the dimension of this space? That's going to be my question that you guys have to answer after the board is erased. What's the dimension of this space of matrices? Write it down, think about it, give me an answer. It is indeed 1. So, skew 2 times 2 has to be the set of things like this. 0 minus a, 0. For a belonging to real numbers. Like this. Yeah? So in our picture over here, this is the rotations. Okay, this here is the identity. And now I'm going to draw perhaps a bit of a smaller ball. This is the ball of radius square root of epsilon. Constant times square root of epsilon. And this is the tangent space. And the tangent space is all multiples of the tangent, right? All linear, it's the vector space created by all the tangents of this submanifold. This is a one-dimensional submanifold. The tangent space is a one-dimensional line, and it's given by this one-dimensional line. Yeah? So skew is indeed this line here. Yeah? Cool. And what we observe is because we have this nice curvature effect of the ball, all the gradients of W inside the ball of radius 1/4 live inside this neighborhood, right? So that distance away from the skew-symmetric matrices is actually of order epsilon. Yeah, because this ball is of radius squared over epsilon, and we have this quadratic curvature here. So we actually get that the distance away from this subspace is of order epsilon. Okay. So, and integral of ball of 1/4 of the distance squared of W away from skew 2 times 2 x 1/2 is less than constant times epsilon. We gain back a power of epsilon right here. Are you with me with this picture here? If you're in any doubt about this, just do the Taylor expansion, write it out mathematically, but it should be sort of obvious. It should be kind of obvious that we are at least curving away quadratically. This isn't a linear distance here. It could be even better than quadratic, but it's certainly quadratic. So this is certainly true. Cool. So we have this. And we're about to invoke a theorem called Korn's inequality. But before this, let's just examine the situation with skew-symmetric matrices for just a second. So notice the following, that if we have A, which belongs to symmetric matrices 2 times 2, and then B belonging to skew-symmetrices 2 times 2, then if we take the dot product of these two matrices, which means we dot product all the entries, what are we going to get here? What will we get here? So when I write this, I mean the sum ij equals 1, 2, or whatever the dimension is, of aij, bij. Yeah? This is the dot product of matrices. So we dot product a symmetric matrices and a skew-symmetric matrices. This is 0. Because what happens if we dot product something that's symmetric, then this entry and this entry contribute nothing. Yeah? And these guys for symmetric matrices are the same. So we'll just have B times A minus B times A. So this dot product is 0. So then this thing is 0. This is a subspace. Skew-symmetric matrices are subspace. Symmetric matrices are subspace. This means that they are orthogonal subspaces. Yeah? They are orthogonal subspaces. Yeah? And in fact, we can decompose. So for any matrix A, B, C, D, or why not A, B, C, D, we can write it like this. We can go A, B plus C over 2, B plus C over 2, D, and that's a symmetric matrix. And we have 0, we can have B minus C over 2, we can have minus B minus C over 2, and then 0. Yeah? And then this is the sum of the symmetric and the skew-symmetric. This gives the same thing. Yeah? Cool. So we can project onto symmetric or skew-symmetric matrices with these nice linear operators, which are given explicitly with their coefficients right here. Yeah? So we're going to call this thing projection onto the symmetric matrices. So let's call this matrix A. This guy is the projection onto the symmetric matrices, and this guy is the projection onto the skew-symmetric matrices, like this. And they're orthogonal projections. Yeah? And this makes sense, right? Because symmetric matrices are a 3-dimensional thing, skew-symmetric matrices, 1-dimensional line. So we have this orthogonal projection. Yeah? And we'll need this shortly. Everybody with me? Yeah? Cool. All right. So we reduced the problem down to this thing right here. Yeah? And now there's a very strong and powerful inequality, which I will ultimately prove, but only a special case initially, called Korn's inequality. So and that's the following. So it's in n by n. I'm going to do this in 2i2, of course, but Korn's inequality is as follows. That given u from omega contained within Rn to Rn, then the infimum over all skew-symmetric matrices. So from now on, I'm just going to write skew, and I'm not going to write the dimension anymore because it's going to be clear from the context of the gradient minus a is less than integral of omega of the distance of the gradient of u away from the skew-symmetric matrices squared 1 over 2 with some constant c, of course. And the constant c just depends on the dimension and the domain. Like this. Okay, so this constant is independent of the function, right? So for any function, its distance away from a fixed matrix inside the skew-symmetric matrices is controlled by its L2 distance away from the whole subspace of skew-symmetric matrices. Yeah? So this statement is very similar to the statement of Muller's theorem, or Friesecke James Muller theorem, except that now we have this much simpler subspace of matrices. This is a linear subspace. Yeah? So we can actually think of Friesecke James Muller theorem as being a nonlinear generalization of Korn's inequality, because it's exactly the same statement. Yeah? It's exactly the same statement. Cool. All right, so with this inequality, we are now very happy because we have this is true, right? We have this is true. Yeah? So applying Korn's to W, there exists A belonging to skew. Out of consistency now, I'm going to say skew 2 by 2. I said I wasn't going to. Such that integral of ball 1 over 4 of this thing, gradient u minus gradient w, is 1 over 2. Okay. This is Korn's. Like this. So this is the statement of Muller's theorem, except now we have the linear space of skew-symmetric matrices instead of rotations. So let's write it like this. Like this. But this thing is controlled. Now, let's just put it here, c times epsilon. Like this. Yeah? So, if we had that A was a rotation, then this would be exactly the statement that we want, right? This would be exactly the conclusion of Muller's theorem on a subdomain, Friesecke James Muller theorem on a subdomain. Yeah? But we don't have that. We just have that A is a skew-symmetric matrix. Yeah? But we also know that since this is the case, yeah, and all the gradients live inside this ball of radius square root of epsilon, yeah, then that skew-symmetric matrix has to live somewhere also inside this ball of radius square root of epsilon, right? So A could be right here. Yeah, A could be right here potentially. but it has to be inside here since all these gradients are inside this ball of radius squared of epsilon around the identity. Yeah? And A belongs to the ball of radius c times square root of epsilon around the identity. Yeah? Now I claim that we can replace the A by a rotation and have this is still true. And it follows from this picture. So look at this picture. What rotation do we want to replace A by and still have this inequality be true? If we just took the closest rotation to this guy, to the skew-symmetric matrix, then that distance will be less than epsilon, again, by the same reasoning. Yeah? Yeah? So from this, so there exists some R0 belonging to the space of rotations such that A minus R0 is less than a constant times epsilon. Yeah? And then just by triangle inequality, we can put it into this thing. Yeah? So let's call this thing star star. So into star star implies that this is true. Are you happy that I can do this once I have this, or shall I write this out? All we're going to do is we're just going to break this up with the triangle inequality. Yeah? Give me a thumbs up if you want me to write this out. Are you all happy with it? Yeah, we just break this up into gradient of W minus R0 plus R0 minus A, apply the triangle inequality. Then we're just going to have the L2 norm of R0 minus A. These are constant things, so it's just the absolute value of A0 minus of R0 minus A, which is less than epsilon. But we do still find the rotation, and that's the statement, right? So we had initial control of order epsilon, we get back control of order epsilon. Yeah? Except it's on a subdomain, but by a covering argument, we can make the subdomain as big as we like. So if we have any region, then take any subdomain like this, then we can just cover it with balls and then find the gradient for which it's drawn those balls, and then the distance between the overlapping regions where these gradients happen has to be less than epsilon. So we find out how many balls, we do the triangle inequality, find out how many times. So it's enough to control a ball of radius a quarter in order to get any subdomain with just a different constant. And that's just a little exercise in triangle inequality. So this proves the cut down version. To prove the full version, you have to apply some Hardy inequalities. It's not particularly hard, but we're going to just stick with this because this is already strong enough. Yeah? Cool. All right, so what were the steps? The steps were we had our initial function. Yeah? It kind of solved a rough PDE with the right-hand side not exactly being 0, so it solved this rough PDE. Okay, where this right-hand side is kind of small in some sense. Yeah? Then we stripped off the right-hand side so that we could deal with W, which had the same properties, but it was Laplacian. Yeah? Yeah. We use those very special properties. So Z was this guy. So Z was this guy that solved this. Oh, this should be minus here. Z solved this thing. Right? And then we let W be U minus C, and then Laplacian of W is 0. Yeah? And then Z was 0 on the boundary, and then we could test Z with itself and show that the gradient of Z squared integrated square root is less than epsilon. So Z is the thing we strip away. Z solves, everything solves a PDE, but W solves the harmonic equation. Yeah? And that's really the cool thing that we had. Yeah? Yeah? Okay, cool. And then from this, we use the fact that we have this nice thing, that Laplacian of the gradient squared of W is the second gradient squared of W. Calculation, we've done this. Yeah? This square introduces or loses us a power of a square root power. This loses us a power because testing twice on the right-hand side, we can show that this entire expression in the integral sense is less than epsilon, yeah, because this thing is close to being constant because of this initial assumption that gradient of u is close to being on the rotations. Yeah? So we lost a power from this identity, and there was nothing to be done about this. Yeah? But we also gained an L infinity control because it's harmonic, yeah? Which put us in this position of being within a square root epsilon ball around the identity. Yeah? And then we said, okay, cool. We can look at the tangent space then. And we have the distance of the gradient away from the tangent space is now back in terms of control of order epsilon. And the tangent space is the skew-symmetric matrices for which we have a Korn's inequality. It is close to a fixed gradient in an L2 sense with the same order of control. And then a simple argument means we can just replace the skew-symmetric with an actual rotation. So there are multiple steps, but it's actually not that hard to prove. Maybe it's, after all the stuff I went through, it seems kind of complicated. But if you run it through your mind a few times, it actually seems it's actually kind of not that difficult, and it could have potentially been proven quite a long time ago. These tools are not very sophisticated tools. Solving this PDE is not particularly hard. Korn's inequality has been known for a long time, but yeah, nobody proved this before, and people tried. This was an open problem for quite a long time. So. Kind of just shows you how that even open problems are accessible with the right combination of methods, using techniques that are around for a long time. Yeah? And again, this is one of the rare instances where we can prove a deep theorem about elementary mathematical objects that were understood and known to our mathematical ancestors hundreds of years ago. And those are really the kind of statements I like. And these are the jewels in the mining of mathematical results. For me, the real diamonds are when you can say something interesting and new about mathematical objects that are elementary that you could explain to an undergraduate even. All right, cool. So that is how we prove it. But a lot of the heavy lifting was done by this thing, by Korn's inequality, which is a linearized version of Muller's theorem, or better to say Friesecke James Muller theorem is a nonlinear version of Korn's inequality. So I want to give you at least a little bit of ultimately I want to prove this to you if I can squeeze it in with the time constraints. But I at least want to give you a flavor of how we can get this kind of stuff. And it's also an excuse to talk a little bit about Fourier series and Fourier transform, which are these extremely powerful things that you can't hear too much about if you're going to do analysis in any field. We are using Holder's inequality in several places, and there isn't a Holder's inequality for p equals 1. There is a weak control where you accept the loss of a logarithm. So if p equals 1, then this is the statement of Muller's theorem that the integral of omega of the gradient of u minus the fixed rotate. Okay, let me write it this way. If we let epsilon, so let epsilon be the integral of omega of the p equals 1 distance of the gradient of u away from rotations like this, there exists some rotation R such that the integral of omega of the gradient of u minus this thing dx is less than constant log epsilon to the minus 1 times epsilon, like this. So we lose a logarithmic factor here. And I think that's a common phenomena when you have an inequality for LP and you want it for L1, that you can have it, but at the cost of a logarithmic loss of power. And this is actually sharp. You can't do better than this in L1. You can't do better than this in L1. It's also sharp for Cohn's inequality, that you don't have anything better than that in Cohn's inequality in L1, and that's sharp. And there's a paper by, well, it probably doesn't matter to you guys, but there's a paper by Friesecke, Maggie, Conti, I think those three guys, exactly on this, saying sharpness of Ornstein type inequalities. Okay, now the counterexample is quite nice, quite neat, and quite simple. All right, so Fourier series, actually we probably don't have any time. So this is what I'm going to do in the next class. I'm going to talk a little about Fourier series, then I'm going to talk about Fourier transform, and then we're going to prove the following thing, following version of Cohn's inequality, that so if we have a function u that is defined, so we're going to say it's like C1 of compact support from R2 or into R2, then the integral over the entire domain R2 of the gradient of W squared dx is controlled by a constant times integral over R2 of the norm of the distance away from the skew-symmetric matrices. The distance away from the skew-symmetric matrices, since we have that the skew-symmetric matrices and the symmetric matrices are orthogonal subspaces, we can represent the distance away from the skew-symmetric matrices as simply the projection, or the norm, or the absolute value of the projection onto the symmetric matrices. So I'll write it like this: a projection onto the symmetric matrices of the gradient of W, like this, squared. And you might think, okay, where is the skew-symmetric matrix here? Well, the skew-symmetric matrix you can think of as the average of the gradient, but the average of a gradient of something which has got compact support like this is going to be 0 just by fundamental theorem of calculus. So that is a version of this thing, and we're going to prove it via the Fourier transform and some basic algebra. And after I teach you a bit about Sobolev spaces, I can prove actually the Cohn's inequality we need reasonably easily as a consequence of this guy. So for Wednesday, look back at your notes from when you did a course. I'm assuming you all did courses on PD and Fourier analysis. We have one at UC. It's like a standard course for most undergraduate places. So look back, review a little bit about those topics, because we'll use some basic properties, and we'll see how this is proved. And then after that, I'll talk about Sobolev spaces and some more background for the stuff we need. All right, have a great day, people. I will see you all on Wednesday. Bye-bye.